So good afternoon students. Today class I am going to discuss about the other law of vector addition. So in the previous class we come to know that we can add two vectors by using two laws of vector addition. One is triangle law and one is parallelogram law. If by using parallelogram law we can find the result out of any two vectors easily by calculating the result of two vectors. We have calculated what? Magnitude and direction. So to calculate magnitude of resultant of two vectors, what is the formula we have? R equals to a square plus b square plus 2ab cos theta. So by using this formula we can find the magnitude of resultant of two vectors acting at any angle, and we can find the resultant direction of the vector by using the formula tan alpha equals to b sin theta by a plus b cos theta. What is theta here? Angle between two vectors. So we have discussed different cases when the two vectors are parallel, perpendicular and anti-parallel or at any angle. Now we can get a doubt that what is the question we can arise? Sir, in the previous class we already discussed only we can add two vectors or subtract two vectors by using these two laws of vector addition. But I have more vectors. I have more than three vectors. How can we add? Can it is possible to obtain the resultant of two vectors by using these laws? No. We cannot use these laws of vector addition for adding more than two vectors, because here the variables are a and p. So we can introduce only two vectors. So there is a need to go for another law of vector addition. What is that? That is called what? Polygon law of vector addition. What is that? Polygon law of vector addition. What it says that polygon means any regular shape having more than four sides we can represent as polygon. So the same thing we are going to convey here, that if I have more than two vectors, what can I do here? According to this law, if number of vectors can be represented in magnitude direction by the sides of a polygon takes in same order, then the resultant is represented in magnitude and direction by the closing side of the polygon taken in opposite order. So I will repeat the statement as here: if number of vectors, if a number of vectors represented in magnitude and direction by the sides of a polygon, then what you can say that should be arranged in some regular order. So what can we write here? For example, I have three vectors. Now I am taking three vectors here. One is a bar, and the one is b bar, and one more is like this, it is present c bar, and one is d bar. Now I have four vectors. We cannot add these four vectors by using parallelogram law. So what this statement has been saying, that if there are number of vectors having magnitude and direction, so we cannot place all the vector like this. So we should place all the vectors in one regular order. What is the regular order? That is what we done in triangular. So we should connect head to tail. So next one is what? B bar. Let us arrange in regular order as the tail is connected to head. One more. This is C bar. Next one. And this is what? D bar. Now I connected all the sides of the vectors in regular order. That is head to tail, having magnitude and direction. Then according to the statement, it explains that the closing side of the polygon gives resultant vector in opposite order. See here, opposite order means what we have to do here? We should connect. Here how we connected? Head to tail. Here also head to tail, tail to head. So we should connect. Opposite order means what? Tail to tail, head to head. So this gives what? Resultant vector. So that is what the statement we have got is, if a number of vectors represented magnitude and direction by the sides of a polygon, then the other side gives a resultant vector in opposite order. Okay, let's see the statement. See the statement. If a number of vectors can be represented in magnitude and direction by the sides of a polygon taken in same order, then the closing side of polygon gives resultant vector in opposite order. Let us see. Let us calculate the resultant of these 4 vectors what we have taken. How to calculate? Let's see that. This is A bar and this is B bar, C bar and D bar. Okay. Now, first let us take that only 2 sides of a polygon. Means these 2 sides represents 2 vectors having magnitude and direction. Then the closing side of this one, triangle, means we are inducing triangle law in polygon law, right? So this gives what? Resultant vector, that is A bar plus B bar. Is it right? These 2 represent 2 sides of a triangle. Then the third side gives the resultant vector in opposite direction. Now again this A bar plus B bar and C bar are 2 sides of a triangle. Yes, this A bar plus B bar and C bar means this is A bar plus B bar and this is C bar. Then this is the closing side which gives the summation of these 3, that is A bar plus B bar plus C bar. So now I am going to get the resultant of these 3 here, A bar plus B bar plus C bar. At last, now again last one, these 2 sides represent 2 sides of a triangle. Then this closing side in opposite direction gives the summation of all 4, A bar plus B bar plus C bar plus D bar, that is the resultant. So this is the way to calculate the polygon law of vector addition, or the addition or subtraction of more than 2 vectors by using polygon law of vector addition. Now we completed how to types of products of vectors, right? Dot product and cross product. Next, addition of 2 vectors or more than 2 vectors, addition or subtraction of more than 2 vectors. Now I am going to continue this topic by multiplication of vector by a scalar. Multiplication of a vector by a scalar means, or a scalar by a vector, you can take anything. Multiplication of scalar by vector. As we know, scalar has only magnitude, right? So if you multiply a scalar with respect to a vector, what may happen? Is it right? That is the question. So what are the things is going to change in vector? We know that what is a vector? Vector has both magnitude and direction. So if you multiply a scalar, what it may happen? Let's see here. See, when a vector is multiplied by a scalar, what happens? The magnitude of vector changes. The magnitude of vector will changes, but not its direction. See, when you multiply a scalar by a vector, there is change in its magnitude but not its direction. Let us consider there is a vector a bar. I multiplied this vector with a scalar called lambda. Then the resultant is what? A bar or a dash is equals to what? Lambda times of a bar. Means, for example, I have vector a bar. We multiplied the vector a bar with scalars 2, 3, minus 1 by 3. Is it right? So what happens now? In each case, first case 2 a bar, this becomes 2 times of a bar. 3 a bar, this is 3 times of a bar. Minus 1 means this is minus a. Minus 1 by 3, this is minus 1 by 3a. So in each and every case, when you are multiplying with scalar, its magnitude changes but not this direction. Here we can get that out. Sir, you said that here it changes its direction. It just reverses its direction but not changes its direction. For example, can it become a bar like this? No, right? A parallel vector cannot become a perpendicular vector. It can be happen when we do vector multiplication, we can change the direction, but by scalar multiplication we cannot change the direction. One more example, if we take this here, when we multiply vector with negative value, it reverses its direction but not change its direction. So there is a lot of difference between reversing its direction and changing its direction. So changing its direction may be it can be rotated to any angle, but here it can change its direction either to positive or negative when if you multiply with as negative value. For example, when k or lambda is equals to 0, the vector becomes 0. It also becomes what? Null vector. But we know very well what is null vector. A vector whose magnitude is 0 and indefinite direction is called what? Null vector. So by multiplying a scalar with vector, we can change its magnitude and we can reverse the direction, but we cannot change its direction. For example, let us consider a vector as we said that a bar equals to I cap plus j cap minus 2k cap. Now multiply with 5. So what it becomes? 5 into I cap plus j cap minus 2k cap, that equals to what? 5a cap plus 5j cap minus 10k cap. So along each axis we can observe that there is a increase in its magnitude because it is multiplied by a factor 5. So when you multiply a scalar with a vector, we are observing the change in magnitude but not its direction. So this is the way to calculate or the concept of what? Multiplying vector with scalar. So with this we come to know that how to do product addition of two vectors and what happens when you multiply scalar with a vector. Now coming to some vector quantities, what we know in that I am considering that position vector. As we learnt in the first chapter, what is position? If a particle is in straight line, it has only one position and one direction. So no need to bother about the unit vectors. But when the same particle moving in a plane, it can move at any axis, either x axis, y axis or z axis. For example, there is a particle that is moving in a plane. Let us take that. I want to know the position of this particle. So what we have to do? We should draw coordinate axis. So this is in two direction, x, y and z axis. So the position of the particle with respect to origin is what? Let us assume that x1, y1 and z1. So this is, I consider that position of the particle initially is what? r1. This is the position of the particle with respect to origin. Now after some time, it travels the distance to r2. Now the position coordinate has been changed, right? x2, y2 and z2. So this is the position of the particle from origin. Now what is the displacement? As we know very well, the shortest distance between initial point and final point. What is the initial point? r1. What is the final point? r2. So this is displacement. What is displacement? The shortest distance between initial point and final point. Now it is in a plane. What is the position coordinates I can write here? r1 equals to x1 I cap plus y1 j cap plus z1 k cap. Similarly, r2 equals to x2 I cap plus y2 j cap plus z2 k cap. What is displacement? The shortest distance between initial point and final point. So the displacement can be written as delta r equals to r2 bar minus r1 bar. So r2 minus r1, we can subtract the vectors which are traveling along same direction. So what you can write here? x2 I cap plus y2 j cap plus z2 k cap minus x1 I cap plus y1 I j cap plus z1 k cap. So subtracting these two, what you can get here? x2 minus x1 into I cap plus y2 minus y1 into j cap plus z2 minus z1 into k cap. So this is the vector or the displacement of the particle that is moving in 3 dimensions. If I want to calculate the magnitude, what is the magnitude? We should write in modulus, right? Under root the coefficient of x axis square plus y axis square plus z axis square. So what you can write here? x2 minus x1 whole square plus y2 minus y1 whole square plus z2 minus z1 whole square. So this is the magnitude of resultant vector which is moving in a plane. So to understand this one, let us take an example. What is the example we can take here is, let us take that a bar is the initial point of a vector, okay? Or you can take the same vectors, r bar is equals to 2 I cap plus 3 j cap minus k cap. r2 equals to 5 I cap plus 6 j cap minus 2 k cap. Okay. Now what is the position vector? Delta r is equals to r2 minus r1. So subtract this one, 5i minus 2i, or what is x1 here? This is x1, y1 and z1. This is x2, y2 and z2. What is the formula we have? x2 minus x1 into I. What is x2? 5. What is x1? 2 into I cap plus y2. Y2 is what? 6. Y1 is 3. 6 minus 3 into j cap z2 minus 2 minus of minus plus 1 into k cap. Just subtract 3i cap plus 3j cap minus 2 plus 1 minus k cap. So, that is the position vector or displacement of the particle. If you want the magnitude, delta r is equal to root of 3 square 9 plus 9 plus 1. So, you get root 19 units. So, this is the way to calculate the displacement of a particle that is travelling in a plane. Next class we are going to discuss about the velocity, acceleration and some other concepts. Thank you.